In the notes for Module 11, we deal with similarity and transformations. So in order to understand similarity, we have to get into our last transformation. We've already covered our rigid motions, which were translations, reflections, and rotations. But now we also get introduced to the non-rigid motion, which is a dilation. A dilation starts from a center of dilation, which is a fixed point, and basically your polygon would either expand or shrink based on a scale factor. Scale factors that are greater than 1 means that your polygon would get bigger. A scale factor that's between 0 and 1 would cause your polygon to shrink. Some properties of dilations. Here are some things that you should know. They preserve angle measure. They preserve betweenness. They preserve collinearity. They preserve orientation. Basically, we learned that before with rigid motions preserve size and shape. Dilations preserve shape. That's what they're referring to here. Like our polygons are still going to look the same shape, but what's going to change is the size. So dilations map a line segment to another line segment whose length is the product of a scale factor. So the way that these polygons are getting bigger or smaller are by multiplying. If you multiply by a number that's bigger than 1, you get bigger. If you multiply by a number between 0 and 1, you get smaller. Dilations map a line that's not passing through the center of dilation to a parallel line and leave a line that's passing through the center the same. So if on your polygon, if one of the sides is not passing through the center of dilation, then when the dilation is finished, the resulting image is going to be parallel to the where the segment was originally in the pre-image, unless it is unless the side is passing through the center, and in which case if it passes through the center of dilation, the line itself, the size is going to change, but the line itself would be in the same position. So if we understand dilations, now that leads us into similarities. So similar polygons. I could somewhat compare this to congruent polygons. We learned earlier in a previous module that if two polygons were congruent, the sides were congruent and the angles were congruent. Polygons are made up of sides and angles, and they were both congruent. But with similar polygons, and you see here the symbol for similar, almost even looks like congruent. When you had a congruent polygon, it was the little mustache with the equal sign. But now, if you lose the equal sign, that means similar. On similar polygons, corresponding angles stay congruent. Just like with congruent polygons, the angles are congruent. We're preserving angle measure, but the sides are proportional. Instead of being congruent, we change the word for sides to proportional. If you look here at the example, since these are a result of a dilation, and dilation means to multiply, and the inverse of multiplying is division. If I were to get the corresponding sides, like 5 corresponds to 2.5, 6 corresponds to 3, 8 corresponds to the 4, and 10 corresponds to the 5. If I were to divide all of these, I would get the same ratio. 5 divided by 2 is the same. 5 divided by 2.5, that should be 2.5, is the same as 6 divided by 3, and that's the same as 8 divided by 4, and that's the same as 10 divided by 5. And you might look at this and say, whoa, but hey, these don't look the same. But they are the same. If you divide each of these, you get 2. They are all equal to 2. Oh, oops. All equal to 2. And this is another graphic that just says the exact same thing. Instead of with a quadrilateral, this is with a triangle. Notice how corresponding angles are congruent, and corresponding sides are proportional. This is what I just finished doing, where if you divide each of the corresponding sides, they abide by the same ratio. A proportion is just two equal fractions. So when I say proportional, any number of fractions, as long as once you divide, you get the same number, those are proportional. And finally, some shortcuts for triangle similarity. Just like with triangle congruence, we had the shortcuts. We had side, 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 angle, angle, side, and angle, side, angle. We have shortcuts for triangle similarity. The first one is angle, angle. There's no need to call this angle, 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 because we already know that when two angles are congruent, the third angle has to be the same. That's called third angle theorem. So instead of calling this angle, 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 which I guess you could call it angle, 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 but we just call it angle, angle. So if two angles in one triangle are congruent to their corresponding angles in another triangle, that means that the triangles themselves are not congruent, they're similar. This is another example of angle, angle similarity. Here, triangle ABE is congruent to triangle ACD. This is a very common type of angle-angle similarity when they put one triangle inside of another one. And the reason why they're similar is due to angle-angle similarity. If these sides, BE and CD, are parallel, that means that their corresponding angles are congruent, and B corresponds to C, E corresponds to D. Those are congruent, therefore the triangles themselves are congruent by angle-angle similarity. Side, side, side. Now don't get this confused with side, side, side congruency. This is side, side, side similarity. With side, side, side congruency, the corresponding sides were congruent, but here the corresponding sides are proportional. So if you were to divide each of the corresponding sides and they abide by the same ratio, then those sides are proportional. You can prove that two triangles are similar by side, 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 proportionality, side, side, side similarity. And the last one is side, angle, side, where now we have two sides that are proportional because sides are proportional, and we have one angle that is congruent. And not only that, but we also learned from before when we did congruency that angle, in order to be side, angle, side, that angle has to be in the middle, which we call included. So if two sides are proportional and the included angle is congruent, then those two triangles would be similar, not congruent, they would be similar, and they would be similar by side, angle, side similarity.